NASA decided to kick off the year in a major way, by performing the latest test on the core stage engines of the Space Launch System, destined to put the first woman and next man on the moon. In this video, we are going to look at NASA Space Launch System, the most powerful rocket ever made. So it comes as no surprise, that after almost 50 years NASA is sending the first crewed mission back to the lunar surface since Apollo 17. This time utilizing the Artemis Program, which is a series of lunar missions that will be the catalyst for future explorations beyond the moon. But how will we get back to the moon, or even further out into our own solar system? NASA has been prepping its new SLS rocket, and working with partners to build a new crew capsule known as Orion. In addition to the capsule, SLS can also carry astronauts and cargo to the moon in a single mission. But the rocket wasn't just designed to get humans back to the moon. In fact, it's the first deep space rocket developed for crewed missions by NASA since the famous Saturn V rocket, which was used for the Apollo program. NASA defines the design of SLS as flexible and evolvable, which will allow for longer scientific robotics missions deeper into space. This is possible because of the multiple configurations of SLS that can achieve not only various payload capacities, but also maximum thrust, making it adaptable for crewed and cargo missions to the moon as well as other planets. Standing at roughly 64 meters tall, the core stage of the SLS contains more than 2.7 million liters of propellant. Broken down into 5 major sections, each plays a critical part in the success of the mission. The top of the core stage, or the forward skirt, holds the onboard flight computers and avionics, which is basically the brains of the rocket. The liquid oxygen and liquid hydrogen tanks each contain cooled propellant, clocking in at roughly 2 million liters of liquid hydrogen and about 742,000 liters of liquid oxygen. Joining the two tanks together is the intertank, which also functions as an attachment point for the forward booster, and holds some onboard electronics for the core stage. Finally, channeling the propellant from the tanks into the 4 RS-25 engines is the engine section, which also functions as the avionics needed to steer the engines. Together, this system produces a total of about 8.9 meganewtons of thrust, accelerating SLS to a speed of Mach 23. The real engineering genius behind SLS is that NASA has incorporated technology and lessons from past crewed missions into the different configurations for SLS. Most noticeably, is the famous orange foam-covered external tank, which was seen on shuttle launches and is used in the core stage of the SLS. And as for power, when compared to the Saturn V's 34.5 meganewtons of thrust, the smallest configuration of SLS puts out a hefty 15% more thrust. Which leads us to the partially successful test of these retro engines. Just recently NASA conducted the 8th Green Run Series test on the RS-25 engines of SLS. Which is basically a series of evaluations to guarantee the completed system is primed for flight. This specific test requires the engines to fire for a little over 8 minutes, which mimics the amount of time it would take to launch SLS into space. And this test is known as the hot fire test, for obvious reasons. Despite completing several operations, the Green Run team has decided that an approximately 4-minute test would give them all the necessary data to confirm the core stage and engines are fully prepared for a real flight. A decade in the making, the core stage for NASA's first Space Launch System heavy lift rocket rolled into the Vehicle Assembly Building at the Kennedy Space Center, Thursday, to join up with twin solid rocket boosters and an Orion capsule for an unpiloted test flight around the moon. Clad in orange foam thermal insulation, the 212-foot-long, 64.6-meter rocket rolled off NASA's Pegasus barge, Thursday morning, on a transport cradle driven by a self-propelled mechanism that carefully drove the core stage the nearly half-mile distance, from the turn basin to the south door of the VAB. Ground teams took their time with the operation, moving the rocket along at a glacial pace after an issue with the self-propelled transporter delayed the start of the offload from the Pegasus barge by about 3 hours. Finally, the rocket emerged at around 8:30 a.m. Eastern Daylight Saving Time Thursday from the Pegasus vessel, a specially designed barge that once hauled external fuel tanks for space shuttles, from their factory in New Orleans to the Florida launch site. NASA extended the length of the barge to 310 feet (94.4 meters) to fit the longer SLS core stage. The Boeing-built core stage measures 27.6 feet (8.4 meters) in diameter, the same width as the shuttle external fuel tank. The gigantic core stage contains reservoirs that will hold more than 730,000 gallons of super-cold liquid hydrogen and liquid oxygen propellants for launch. 4 Aerojet Rocketdyne RS-25 engines are affixed to the rear of the core stage. All 4 engines are veterans of multiple space shuttle missions. Engineers test-fired the 4 RS-25 engines for 8 minutes March 18 at the Stennis Space Center in Mississippi, the same duration they will burn during a real launch. The hot fire was a final development test intended to iron out any glaring issues on the core stage before the first SLS test flight, known as Artemis 1. Officials at Kennedy are eager to start working with the core stage inside the VAB. The two 177-foot-tall, 54-meter, solid rocket boosters for the first SLS test flight, supplied by Northrop Grumman, are fully stacked on the rocket's mobile launch platform in High Bay 3 inside the vehicle assembly building. With the core stage now at Kennedy, technicians will complete refurbishment of the rocket's foam and cork insulation, which suffered some expected damage after the 8-minute RS-25 engine test firing last month. Ground teams at Kennedy will also install ordnance to be used on the rocket's flight termination system, which would activate to destroy the rocket if it flew off course and threatened the public during launch. NASA aims to be ready by the end of May to rotate the rocket vertical and lift it by crane into High Bay 3. A crane operator will carefully lower the core stage in between the two SLS solid rocket boosters. And hopefully, we'll be using SLS to get to the moon and beyond. Make sure to subscribe and thanks so much for watching.